Hello, everyone. It's my great pleasure to present here. And I'm Xiaozhen Qian, and you can call me by my Korean name. And today I'm going to present the part of my research. And the topic is the impact of tropical cyclone motion on stone surge and compound flood in coastal areas. Uh, so compound flooding actually poses a major threat to the coastal areas, like especially during the tropical cyclone events. And this type of flooding is caused by the combination of the storm surge, high tides, and heavy rainfall from and induce the inland water level rise, and which these two water sources from the seawater and the inland water will together and can result in heavy flooding. Another terminology in my topic is about the tropical cyclone motion. And in this presentation, I will focus on how the tropical cyclone movement will affect the stone surge and how its rainfall will affect the compound flooding. And with a specific emphasis on the effect of the translation speed and the landfall angle, these two factors. And while these two factors will alter the distribution of the wind and pressure field and also the precipitation field. Also, actually, there are other factors. It will affect the stone surge and the flood, which is the topographic features. But in this presentation, I will just focus on the tropical cyclone motion features. So why do we need to consider the TC motion in stone surge event? Actually, there are some studies have reported that in the future, the tropical cyclone translation speed will slow down, and it will also means the rainfall will lasting long time. And this phenomenon can change the risk of the coastal hazard. And when the TC motion changes, what will happen to the wind pressure and precipitation field is the question. And how it will affect these two events is also our focus. So our study will firstly cover the contents of generation, the future TC checks, and with their wind pressure and rainfall field by using some models. And we aims to generalizing the effect of the TC motion on the stone surge, and we expect it to form a simple and quick evaluation guidance. And since the compound flood is not easy to be generalized, we plan to investigate it in a certain coastal basin. So in this presentation, I will divide the contents into two parts. One will focus on the wind and pressure induced stone surge, encompassing different TC motion scenarios, and another one will focus on the various moving TC rainfall generation and how compound flood affected by it. So this is the first part about the effect of the TC's translation speed and landfall angle on the stone surge dynamics. So this is the in the figure we can find the definition of the landfall angle, and this is the coastline. So this is in the right hand. The angle is right hand angle between the landfall check and the coastline. This figure is the numerical domain, and another figure represents 5 different bathymetry we will use. All the cases are the idealized cases because we want to generalize the effect. So we need the idealized cases. It's not easy to using realistic cases to conclude something. Only if we focus on a certain area. So these idealized cases will consider the landfall angles from 0 degree to 180 degree, and the translation speed in like about 7 types. And so these are the cases designation. And in this presentation, I will just present the result about the open coast cases. These cases will simply show us how the landfall angle and translation speed affects the stone search. But we also run many other cases like the bay cases and the realistic cases. This is to show how the topographic features and the TC motion characteristics integrity affect the stone search. And as I mentioned, we need generate the checks in the future. We need, if we want to get some evaluation of the future scenarios, we need a simple, not simple, but like the model to get the future wind and the pressure under the typhoon. So in this case, we use a famous parametric model, which is the Holland model. And if we have the noise variable, like the maximum wind speed and the minimum pressure, then we can get the wind field. And these are the results from thousands of cases. And these figures show the result for the constant seabed cases with different landfall angles and different translation speed. As we can see, we can find 2 basic findings. One is that as the translation speed increase, the maximum surge height will also enhance. And another one is that this trend, the MSH trend, the maximum stone surge height trend, actually have a arch-like pattern, and we can find the peak at when the landfall angle is about 90 degree. But if you look at some scenarios with relatively slow translation speed and small angle, there are different patterns. So we need to know what happened to them. So we plot other types of figures. This is the water level along the coastline at every time step. For this first panel, we can find the pattern of the coastal Kelvin wave. And this Kelvin wave will trap the energy, and it will result in the decreasing trend in previous MSH trend. So actually we run lots of cases, and then we get this very, I think it's beautiful. Yeah. So this is the factor-based diagnosis diagram, and it shows that if we check the translation speed, and then if the it has 2 conditions, the slow to the fast. That means when the translation speed increase, the stone surge will increase. So this type of factor-based diagnosis diagram is very quick and simple evaluation guidance for the future scenarios. If we have a future scenario, so like the typhoon will be about 35 meters per second in the maximum wind speed. And now we have many also about that maybe higher than 35 meters per second. That means in the future, this scenario will have a lower stone surge than many cases. Yeah, this is the diagnosis diagram, how we can use. And this is about the part 2. So part 2 is about the rainfall field affected by the tropical cyclone motion and how the compound flood will affected by it. So also in the beginning, we should know how to get the synthetic tracks and the rainfall in these synthetic tracks. We for now, if we do some hand casting cases, we can use the observation rainfall data or from some like numerical model, like the WRF, or from some institute, we can use the reanalysis data. But if we want to do a quick and simple evaluation, we should have our like new method, which can simply generated the TC rainfall and also should cover the rainfall characteristics. So we are thinking about how we can like revise the whole land model, which is the parametric model of the wind field, to the rainfall model. So that means we need use some like okay. Anyway, so we should build some model of the TC rainfall. So actually there are lots of models already extensively used, like the R Clipper and IPET, but they also have some limitations. So recently there are a statistical model based on the Holland model, and they revised it into the rainfall model. Just switch the variables. Like in the Holland model, we use the maximum wind speed, and now we use the maximum rainfall intensity. So we will employ this model, but we also will develop it because it shows the overestimations in the maximum rainfall and also the cumulative rainfall. So the objective of this study is stochastically generates the TC rainfall distribution using the parametric TCR model. And we will consider the relationship between the wind speed and the rainfall. And we will also simulate the realistic hurricane or the typhoon cases to investigate the effect of the rainfall on the compound flood. So these are the materials we have used. This is the data set. This data set has a specific structure, which is the radial structure. That means it gives us the radial profile of the rainfall, the TC rainfall. And if we check the relationship between the maximum wind speed and the maximum rainfall intensity, we can find it's not really the linear pattern. So we want to do another analysis to get the relationship between these two. So we will adopt the method. Like, so we need switch the variables, the maximum wind speed to the maximum rainfall. And this is our model, the previous model, Bader's model. And in our model, we will add another effect from the translation speed. And we use coupler method that can help us to find the relationship between the maximum wind speed and the maximum rainfall intensity. So once we find the relationship, then we can revise this formula to our model. So this is the flow chart of our work to generate the TC rainfall. So first we collect the data, and then we find the individual distribution of Vmax and Imax, and then we use the coupler, find the best coupler in the coupler families, and we find that the best one is the Frank coupler, and we adapt this, and we should do the conditional sampling and get the certain Imax. If get the Imax from for a certain at the certain Vmax. So like if we have information of the Vmax, like the Vmax is at 65 meter per second, then we should have a Imax. So what will be the Imax? We will then we will use the percentile, because we do in the sampling processes, we have lots of samples. So we need get the only one sample from these samples. So we use the percentile method, and also we apply some optimization processes to get the best percentile, the best. Then that means we get the final Imax, and this Imax will be added into the TCR model, and then we can get our rainfall field. So this is the result for the TCR model. As you can see, the red line is the radial profile from our model, and the previous model, and not to model like our Clipper and IPET, they show the underestimation. But our model is quite similar to the observation in this blue line. Yeah, this is for two typhoon cases. And we will apply our TCR model to the compound flooding. So we run the Hurricane Rita cases, but we need to get several checks. So we should check how the TC motion affect the compound flood. So we rotated our original Rita check to the left and also to the right. And we form several scenarios which can help us read how each sources affect the compound flood. And this is the domain of our numerical model. So this area is located in Texas, is the Sabine Nature's river estuary, river basin, and our domain covers the Gulf of Mexico, and the finest domain was in this basin, and the finest grid resolution is about 25 meter for now, but later we will also improve our model. So this is the simple case example, show the rainfall field what we have get. And these are the results from the simulation. So this is the rainfall intensity at the certain observation point. This is at the upper bay, and another two is for the lower bay. And if we check this result, we can find they have different water rainfall rate, and it will induce different water level. But what we can find is that in some case, the left Rita checks have the highest water level, but it doesn't have the highest rain rate. This is because we also should consider some effect like the geometric effect. But anyway, in this case, we can read the result for the rainfall only case. And another simulation is we put another source. at another source like the tide and the surge. This is the coastal water, and the rainfall will give the inland water. So this will form the compound result. So we can find that if we check the compound result at the upper bay, the left result has the largest water level, and the highest water level occurred before the another two cases. To show more obviously, we check the matrix of disturbance, the D. So these represent the inundation depths, and we also calculate the contribution of any forcing component C. So C rain means the inundation depths from the rain-only cases divided by the compound flood cases. So these are the results for the D and C matrix for these left retard cases. And this is for the original retard cases, and this is for the right retard cases. And this plot shows the combination result from previous C and D. So we choose the area of the dominant forcing. So that means we choose the area with C larger than 80%. And then we plot this figure. So the blue shaded area means this area dominated by the tide and surge source, and the gray one represent in this area the compound flood sources is the dominate forcing, and for the yellow one is dominated by the rainfall. So that we can find in the left retard cases, the compound dominates the coastal area most, but the rainfall dominates the land area least compared another two cases. And for these right retard cases, we can find that the compound dominates the coastal area least. So that means if the TC motion is different, it will also cause the different compound flood. But it also depends on the area where we are focusing on. So because the river network is quite different for different basins. So in this case, we just choose this basin. So the result is like this. And this is the summary about this part. So we firstly developed the parametric model for generating the TC rainfall. And then this is based on the Coppola method, which can help us find the relationship between the maximum maximum wind speed and the maximum rainfall intensity. And another thing what we have found is on the impacts of the compound TC motion on compound flooding. So we find that the left TC cases dominate by the stone surge, with the rainfall affecting only the upstream areas, and the extensive compound effects along the coastal line and lower bay. And for the TC from the right hand, we find that rainfall-driven flooding is the most extensive, covering the land, river, and bays. That means if the future typhoon, in this case, landfall at the right angle, it will cause heavy inland water or the inundation depths. So this is will give us some suggestion for the future preparedness for this area under the stone surge event or the typhoon event. And in the future work, we need to consider the validation of our TCR model more, like about the cumulative rainfall. And we also need to reduce our overestimation situation. And second thing is that we need validate our compound flood model also using a higher resolution domain. And these are the remarks of this study. So first, we check about the wind pressure field and how by using this field, we can check how the tropical cyclone motion affects the storm surge. And finally, we get a vector-based diagnosis diagram, and everyone can simply use this diagram to predict or just simple evaluate the future typhoon cases in any area. Yeah. And for another part, we developed the TCR model. This model is quite simple and it can cover the randomness of the TC rainfall. And we also simulate the compound flood events and check how the different precipitation motion will affect the flood. Yeah, thank you.